First of all, I want to thank the organizers for inviting me here. I'm very happy of being here and for this day. And yes, I would like to speak about this to explain the construction of the Floer fundamental group for Lagrangian submanifolds. First of all, the plan of the talk, I will give some background, recall the setting and give some background of Floer homology. And then I would like to go as fast as possible on the main definitions until I reach a statement. And then I will come back on the definition and explain the definitions and give the proof of the main statement. And if I have time, comment on some applications. Okay, so the background is, as usual, I have a symplectic manifold. I suppose it's closed. And it will be at least monotone, but for the beginning, I want to focus on the main ideas of this construction of the fundamental group. So I remove all the Floer issues you have in general. So I don't want any bubbles at the beginning of the talk. So let me focus on the weakly exact case. So I have a Lagrangian submanifold, and I suppose that the symplectic form vanishes on the pi2. And I will discuss what happens if you have bubble later. So it's the most simple setting you can think of in Floer homology. And because I want to do, I want to study a fundamental group, I need a base point. And I need the usual auxiliary data you use in Floer homology. So I need a Hamiltonian function, an almost complex structure that is compatible with the symplectic form. And there will be cutoff functions that will appear just in the next slide. And as it has already been explained several times, once I have this Hamiltonian function, I can consider the flow associated with this Hamiltonian function and begin to deform my Lagrangian using this flow. And I will always draw my first Lagrangian in blue and the second one in red. And this will be a convention all over the drawings here. Okay? And then this was the setting, and then I need some Floer background. I would like to be very fast on that because there is nothing fancy, nothing specific to the construction of the fundamental group here. You can take the description. Of course, there are several versions of Floer trajectories in the Lagrangian setting. I take this one, but because it's good for one of the applications when you do Lagrangian cobordism, but you could take other ones. It works the same way. So let me recall the Floer equation. It's a Floer trajectory is a strip going a map from R cross 0, 1 to M that is J holomorphic, and you have the usual boundary conditions that one side of the strip is sent to L0 and the other side is sent to L1. But we want some variations on that, so will we be using moving boundary conditions? So in fact, the boundary condition on the one side will move along when S moves, and there will be several functions beta. Of course, the first case is when beta equals 1, then you have just the usual Floer trajectories. And another case is when beta is a cutoff function, so it's equals to 1 for S less than -1, let's say, and it's 0 for S greater than 0. And then in this case, I have the same. I always consider a solution of finite energy, so that there are limits at the end. So in this case, it starts like a Floer trajectory, but it ends like a pseudomorphic disk with boundary on L0. And and in this case, oh, I did not say that, but here you can read that the moduli space of strips from Y to X is denoted by M from Y to X. And here I denote this by moduli space from Y to the empty set, by which I mean that I put no constraint on this plus infinity limit of my strip. Okay, this limit, the plus infinity end is free to move on L0. And there will be another situation important to us. The case where, in fact, I take one parameter family of cutoff functions that looks like this. So it's 0 near plus and minus infinity, but it's 1 on a neighborhood of 0 of size essentially R. Okay, then in this case, the trajectory looks something like that. And I put the constraint that on the minus infinity end, it should be at the base point. Okay, this is the kind of moduli spaces I will be using. And of course, there are versions with Hamiltonian chords, like what we have seen before. But okay, these moduli spaces are very classical in Floer homology, and when you do the PSS and so. So I don't know if I should comment more on that. I will draw the trajectories schematically like this, and it saves some room, so I have the space for a fourth situation, which is, of course, the symmetric of this one, when the cutoff function goes from 0 to 1, and then I will get configuration like that start at the base point and end at an intersection point. Okay, all these moduli spaces are just classical objects, as I said, so you know that for a generic choice of the auxiliary data, there are smooth functions, smooth manifolds of finite dimension, and the dimensions can be computed from the topology of the situation. And here I cheat a little bit. Of course, the situation, the homotopy class of the strip, for instance, influences the dimension. But just like what Victor said in the previous lecture, I can go to a covering. So instead of intersection points here, I have intersection points plus some capping of it attached to it. And then the index formulas become correct. Okay, so for the beginning, the most important moduli spaces will be those two ones. When y has index 1, will be one-dimensional, and this one will also be one-dimensional. Okay, so this is for the Floer background. I don't want to insist on that. But now I go to more fundamental group-specific definitions. And I want to define what a loop is from the Floer point of view. And a loop will be a sequence of elementary steps. And a Floer step, is the definition you have here. So a Floer step will be a component of one of the two moduli spaces I pointed on the previous slide, endowed with an orientation. So these two types of moduli spaces, the moduli spaces from an intersection point with index 1 to the empty set, and the moduli space is moduli space from the base point to the empty set, are one-dimensional. So they look like this. So you may have S1 components. We don't care about them. And you may have components with boundary. And this is what I call a step. Or more precisely, to one boundary, to one component, there are two steps. There is a step forward and a step backward somehow. Okay? But this is a definition, but it's not a very human readable definition. So the question is, what does a step look like? And a step looks like something like that. So you have your one-parameter moduli space. So so you can move in one direction. And the only thing that can happen, I didn't say that, the moduli spaces are compact up to bubbling, but bubbles are forbidden for the moment, or break. And the only thing that can happen is that the moduli space, your capping breaks at some intermediate point. So at the end, at one end of my component, I have something like that, a Floer strip in the usual sense, and a capping here, and I tend to call this an augmentation for some reason. Okay, and then when you go into the moduli space, you do the gluing here, and you go there. You got your one-parameter family of trajectories, and of course, the only thing that can happen is the same thing, the same time kind of phenomenon on the other end. And the important thing here is the dashed line you have at the bottom, which is the evaluation at the plus infinity limit. It gives me a path in the manifold. Okay? So this is what a step looks like, at least the steps through the index 1 intersection points. But there are also steps through the base point, and I have to explain that. So let's have a look at this moduli space. If you remember, this should be a 2R here, but it's irrelevant. So the moduli space of trajectories from the base point to the empty sets look like this. They are kind of disks with boundary on L, but for some period, I use the moving boundary condition to go to L1. And of course, the parameter R here is part of the solution. So This moduli space has a projection to the real line using this R factor. And it's particularly interesting to look at what happens when R goes to 0. When R goes to 0, you just have an homomorphic disk with boundary on L, 0. And I said that there were no such things, but in fact, there are always the trivial things. There are the constant disks. So over R goes to 0, you have exactly one solution, which is the constant disk at the base point. And it's not hard to see that this solution is regular, so you really have a moduli space starting there. And there is exactly one component of my moduli space that looks like this. It starts over 0 and it ends somewhere. And of course, the projection is proper, and over R goes plus infinity, you have the break phenomenon. Okay, so I have two new kinds of steps. The first one it looks like this. So I have my constant disk, and I cannot do anything else than artificially somehow growing a disk by using this moving boundary condition. And I let it grow and grow and grow and see what happens. And the only thing that can happen is that it breaks somewhere into a very special configuration of a Floer strip and this augmentation here. Okay, so somehow the base point selects a special configuration like this one. Okay, and for the other one, it's for the steps here, it's very similar. To what we had before, but the only difference is that at the top here you have the base point instead of an intersection point. Okay. Okay. So now we have our three kinds of steps, and if we know what a step is, we can start walking and explore the world, and we can define a loop. So a Floer loop. Okay. A Floer loop is just a sequence of consecutive steps starting and ending at the base point. And consecutive steps mean that, of course, a step is oriented. There is a beginning and an end. And two steps are consecutive. If the augmentation you have at the end of one step is the augmentation you have at the beginning of the next one. Okay? So here, when I glue there, I have one parameter, a continuous family of trajectories. But then when I switch from there to there, it's completely new. It's something completely, it's not correlated to what I had before. The only thing is that I keep this augmentation, but this strip is new. But now when I glue there, I can get one parameter family of trajectories and so on. Okay, and maybe there are steps through the base point. I can avoid them at the moment. Okay, this is the definition of Floer, of a Floer loop. And of course, you can concatenate Floer loops. And if you use the obvious cancellation rule that if you do a step forward and immediately backward, then you can remove this from your sequence. Then this turns the Floer loops into a group. Okay? And moreover, I recall we had this evaluation map that turned each component of the moduli space into a path in L. And now if I have a sequence of consecutive steps, I can concatenate all these paths, and this gives me a loop in the manifold. So it gives me a map from the space of Floer loops to the fundamental group. Okay? Of course, the parameterization of the path I have here is not so well defined. It depends on the parameterization of the moduli space, which have no canonical parameterization. But I'm only interested up to homotopy, so it makes sense. Okay? And now comes the main statement. This evaluation map is a group morphism, and it is surjective, which means that any loop in the manifold is homotopic to a Floer loop, to a sequence of Floer steps. Okay? So, I don't know if there are questions, but I will prove this. But you will see that the proof is very simple, and in fact, it's a case where the math hide in the definition, at least half of the math hide in the definition. So I think I need to give some comments on the definition I just gave of what is this notion of step. Okay, so for that, let me first let's have a look at the Morse case. What happens in the Morse case? So, okay, the beginning is just the Morse setting. You have a a compact manifold, you take a Morse function, a metric, a Riemannian metric. You suppose that everything is generic, so, so that you can look at, you can do Morse theory with that. And there is a well-known description of the fundamental group in the Morse situation. For simplicity, suppose that my Morse function has only one minimum. It makes the description much easier, but it's not essential at this point. Then the fundamental group is generated by the words in letters in the letters given by the index 1 critical points. So, and an index 1 critical point, a letter like that is, in fact, the loop associated to the unstable manifold in one or the other direction. You pick an orientation of each unstable manifold, and y is the loop in one direction, y minus 1 minus 1, y inverse is the loop in the other direction. Okay, this is a well-known fact, and of course you have relations given by the index 2 critical points. But okay, and but I can define Morse loops, which are just the words, the loops associated to these words. So the family of loops you get by concatenating such travel along the unstable manifolds. Okay, and it's well known that the evaluation to the fundamental group is on 2, and the proof of that is, at least with a drawing, very easy. You take any loop in the manifold, and you just push it down using the flow, and it will somehow hang at the index 1 critical point, and this gives you an homotopy between your initial loop and a Morse loop. Okay, so if we want to do that in Floer theory, there are two things you need to understand. First is the basic steps, Morse steps. What is a Morse step in the Floer setting? So one travel along the unstable manifold. And the second is, what does it mean to push everything down? Because, yes, that's the main point, of course. There is no, the two steps I've just described essentially use that you have a flow. You have a Morse flow. If you take any point, you have a trajectory there and you can push. And of course, unfortunately, the Floer equation is not a flow. You have strips, you have solutions of the trajectories of the flow, but you don't have a flow. If you take a path somewhere, it's not, there is no holomorphic strip starting there. It's too much information. Okay? So I have to understand these two things. And so let's so we want to understand this move here. So the upper point is an index 1 critical point, and the lower points are index 0 critical points, and we want to understand what it means to travel along this. And I have to say that this is something I learned from Octave Cornea, and even if you don't care about Floer theory, it's a very nice point of view on the unstable manifold. A good way to think of the unstable manifold even in the Morse setting is the following one. Instead of looking at my red point I had before, I look at this orange thing. Of course, it's essentially the same thing. But instead of looking at the point in the manifold, I look at the trajectory that starts at my critical point under interest and stops at the right point. And it's very interesting when you do Morse theory because, of course, it's the same thing, so you don't see any difference. But it makes a difference when you go to the compactification. Because suppose that these 2 points are the same, if you compactify in the manifold, you get an S1. But of course, the orange thing on the left and the orange thing on the right are completely different. So if you compactify this version of the unstable manifold, you still get a ball. Whoa, sorry. You still get a ball. Okay, so, well, this is not the point that is of interest to us, but the good point for us is that you can write an equation for that. And you can have a modelized space point of view on the unstable manifold. So let me recall the Morse. I call this orange thing an interrupted Morse equation, Morse trajectory, because I follow a Morse trajectory and then I stop. And recall the Morse equation. It's just an ODO. You move with speeds given by the gradient of your function, and you can derive from that the equation for interrupted Morse equation. You just cut off the gradient at some point you multiply by this cutoff function. And what happens near minus infinity, you just follow your trajectory as usual. And when beta decreases and goes to 0, then you start to slow down, and when beta goes to 0, you just stop there. So this is, the solutions of this equation are exactly the interrupted trajectories. So you have an interpretation of the unstable manifold in terms of moduli spaces somehow, okay? And maybe the version I gave of Floer strips is not the one that makes the most obvious that this is a direct analogy with the moduli spaces I've defined, but it is. I did just, in the moduli spaces I was interested in, I did just cut off the boundary condition I had on L1, okay? And it's essentially the same thing. Okay, so, and then when you compactify, of course, it's a different thing, but okay. So I hope that I convinced you that there is an analogy between the Morse steps and the Floer steps. It's essentially the idea. Okay, so at least I understood what the unstable manifold in the Floer setting should be. Okay, now I need to understand what it means to push, yeah. Surjective map, sorry, from where to where? Yes? You mean when I don't take any relations? Because here I've generated, I'm just giving a family of generators, and then of course you divide by the relations. So if the answer, if you have no index 2 critical points, then it's the same. It's already the fundamental group. If you have index 2 critical points, then you have to divide by the boundary of these. Okay, so the next step is to understand what it means to push everything down. And okay, so we already saw, this was a picture on the torus, how to move a Floer loop into a Morse loop. You just push it down. But unfortunately, what we want is to go in the other direction. We want to start with a Morse loop and turn it into a Floer loop. Okay, so I pick a function. Here it's important. I pick a Morse function that has a single minimum at the base point. You will see where it plays a role, but after all, it's just to prove. Now I'm proving that the map is onto. Okay, the evaluation map is onto. And in fact, I could do what I'm going to explain here for this, for the construction of this map C, can be applied for phi, and there is another point of view on phi that fits exactly with the picture I'm going to draw now. But because I'm just interested in this one, let me focus on this one to save some time. So what can we do? We start with a Morse step. So this is a Morse step. It means that we are moving like this. A more realistic drawing would be if this line would go exactly along the Morse line and exactly along the Morse line behind. But I want to see something on my drawing, so I don't do that. So I have this Morse step, and what can I do? Here I have the base point, so I can grow my preferred special step. Okay, and from the base point to this very special configuration. And now I'm looking at a configuration from my Morse critical point to the empty set, essentially, but that uses the Floer situation at the end, and it's broken twice. And when you have a situation like that, you can somehow explore a component of the boundary of this moduli space from, you have a moduli space where nothing is broken here. And you can explore the one boundary component of this, starting from such a point, by gluing, of course, if I glue at the bottom here, I will go back to the base point. I'm going backward. It is not what I want to do. But if I glue upstairs, well, if I glue upstairs, then what does it mean, gluing upstairs? It means that instead of requiring that this point is the base point, I allow it to go along the unstable manifold of Y. You can interpret this as a break of the Morse trajectory. Okay, so I glue there, and I got a one-parameter family of configurations, and it has to do something, and one thing it can do is to break like that. Okay? And now what can I do? I glue at the bottom. And if you glue at the bottom, what you get is exactly a Floer loop here. Okay? This is just what I defined as a Floer loop, a Floer step, sorry. It's a Floer step through this intersection point. And you can repeat the process. You glue at the bottom, and you glue at the top, and you glue at the bottom, and you have a second Floer step. But what can happen, of course, is that, of course, to be more to be convinced, you have to study all the possibilities of breaks for your moduli spaces. And for this configuration, it can break in the Morse setting. It's a picture like that, but it can also break in the Floer, in the Morse part. Or sorry, I started again. It can break in the Floer part or in the Morse part. If it breaks in the Floer part, it has to break between red and blue. We'll see later what happens. But if it breaks in the Morse part, it has to break at an NX0 point, and I required my function had only one. So it has to break at the base point. And the next thing is, again, a step I consider. This is why I need them. I introduce a step through the base point, if you remember. And this is why I need them. Okay? But then I can continue, and because the collection of broken configurations like that is finite, this process has to loop. Because there is no choice. You can glue upstairs, downstairs, upstairs, downstairs. No choice. It has to loop at some point. So it means that you have to reach, after a finite number of steps, you have to reach your special configuration on the other end of the Morse step. And when you glue, you end up in a picture like that. Another way of thinking of that is, as I said, you have this configuration. If you suppose you take one configuration and you take the moduli space where there are no breaks at all, and what we have just described is, it's a two-dimensional moduli space. So what we have just described is an S1, which corresponds to the boundary, one boundary component of this moduli space. But one way of exploring it is by doing these alternating gluings. Okay. And now we end up with this nice picture, and the dashed line is the evaluation of the plus infinity limit. Okay, you can consider there is a trivial disk everywhere here. So there is a plus infinity limit, and you see that you have the Morse step on for one piece, and for the other part is a Floer loop. Okay? And in the middle, you have this kind of disk here. And the disk, okay, the disk can be abstractly defined out of the moduli spaces we just glued together. And this disk has an evaluation to the manifold also, because if you take one configuration, any configuration in this, like this one, you can evaluate along the Morse line and then along the zero side of the strip and until the plus infinity limit. So all this disk evaluates to the manifold, and on the boundary you have the Morse step for one part and the Floer loop for the other one. Okay, so I define the image of this Morse step, which is also a Morse loop in this case, to be the associated Floer loop I have on the other boundary. And the important thing is that the two things are homotopic, because there is this disk in the middle. No questions? This is the crucial part, in fact. Okay, so I have this picture. Well, I call this a crocodile walk if you have a better name. And it ends the proof, essentially, because now, okay, you don't need this part of the diagram. I had my Morse loop, and I know that they evaluate subjectively on the fundamental group. And I have just constructed this map psi to the Floer loops. And we have seen that it's preserved the homotopy class. So it means that the diagram commutes here. So here it's surjective, so here it's surjective. Okay, so it means that the arrow here is surjective. Okay, so this ends the proof that the Floer loops evaluate surjectively on the fundamental group. And now I come to your question about relations. And I'm not very happy with the description I have of the relations. But okay, the first thing is you can describe the relation as being the kernel of the evaluation map. Okay, great. But if you want So what it says is that it does not depend on anything else than the auxiliary data I've used to define everything. But if I want to pick some special generators, then I need to use an auxiliary Morse function. Okay, I hope I can do better, but at the moment I cannot. So in the Morse, I use the same Morse function as before, with a single minimum at the base point. Then it's well known that the relations in the Morse case are associated to the index 2 critical point, and an index 2 critical point has an unstable manifold, which is a disk. And on the boundary of the disk, you see a Morse loop. And these loops somehow generate the relations. And because of the diagram we had on the previous slide, you know that this one, in fact, it's a, if you can go from Floer to Morse, and from Morse to Floer, you can iterate this whatever, in whichever manner you want. So if you know the Morse relation, you will know the Floer relation. And okay, this is one way to do it. You just push down the Morse relation into Floer loops. Okay, this is if you had a Morse relation associated to an index 2 critical point, you turn this into a Floer loop. It has to be a relation, of course, so you take that. And you also take the following thing. If you start with a Floer loop, you push it into a Morse loop and to a Floer loop again, then the two things has to be homotopic, so you put also this in the relations. And then if you take the normal subgroup generated by these things, then you get a group that is isomorphic to the fundamental group. So you can call this the Floer fundamental group. Okay. Okay, that's it. No question? It's a way to define it. I can comment on this later. Now, what about bubbles? So let's try to say one word about the monotone case. And the first thing I want to do about bubbles is to, again, forbid them. So what can happen if you have bubbles? You want to do the same thing. You start with a broken configuration, use a one-parameter moduli space, and see what happens on the other side. And of course, on the other side, what can happen is a bubble. And at the moment, at least, I didn't try it so much, but at the moment, I don't know how to handle these, so I don't want that. I don't want a side bubble. So I will suppose that the minimal Maslov number is at least 3. Then in this case, side bubbling is forbidden just for dimensional reasons. But still, okay, you can have bubbles, inline bubbles, I don't know how you call them. So what can happen, we were considering these kind of situations, and if I glue there, it can break like this. So you see, it's the same picture as before, but the difference is that it broke in the blue part. And the upper component here is in fact a disk with boundary on L0. So this was forbidden before, but now this can happen. And the problem with that, okay, you can say, okay, this is, I used one moduli space, and then I can glue at the bottom with another one, and let's see what happened. But of course, what happened is that the configuration you get here depends on everything above. The point here is not fixed, and the full configuration, you cannot split it in two parts. And in particular, it means that it does not give you a morphism from the Morse loops, to the Floer loops, because this is nothing but this is not a Floer loop, a Floer step. Okay, so what you can do in this setting is you want to stabilize the place where the bubble appears, and you use the Floer the Pearl trick. So what I can do is when I have the bubble here, okay, this is one boundary of my moduli space, but it's also the boundary of another moduli space, which is the space where the two components here are allowed to flow away one from the other according to a Morse trajectory of some preferred function, Morse function I use, I think. So I let them flow, I let them go away one from the other. And of course, many things can happen again, but the new phenomenon is that the Morse trajectory can break. But that's good because this somehow stabilizes the place where the bubbles can appear. Now, when I glue at the bottom, I get something that is completely independent of what happened before. Of course, it means that I have to take these new things as steps if I want to get a morphism. Okay, I have to allow this, but now I can move from the more steps to the new Floer steps. So, okay, so that's what happens when I have bubbles. And the conclusion is that I have to somehow pearlify, sorry for that, the construction. So I take, the definition of a step is the same. It's a component of a one-dimensional moduli space. But the moduli space I'm considering are these ones. The same ones here, but I allow interruption by more strips, by more trajectories are allowed. And I also have to take the index, the most critical points into account, but they are not necessarily, they don't have index 1 in general. Okay. And then a new step can look something like that. But if I take all these moduli spaces into account, then I can still define a surjective map to the fundamental group. Okay, because you still have an evaluation at the plus infinity limit and so. Okay? No, I don't have trees because I don't want to have side bubbling. If I have side bubbling, I will have trees. And then it can break at several places, and I don't know how to do that. Maybe there is a way, I don't know, but I just allow one direction of bubbling, so I always have strips. But they can be interrupted by Morse trajectories. That's all what can happen. Okay. Okay, this one, yes. So maybe I should be quick on this one. I just defined the Floer fundamental group, and I would like to relate this to something you may be more familiar with. Okay, so I will be waving hands, okay. Of course, the main ingredient of the construction is the use of the one-dimensional moduli spaces. It's heavily using that. But in Floer homology, the thing you are all most familiar with is the Floer homology instead of the Floer fundamental. And in Floer homology, there is exactly one place where you do use one-dimensional moduli spaces. It's when you compute d squared, and you want to prove that d squared is 0. When I want to prove that d squared is 0, let me take for, an index 2 intersection point, for instance. Then when I compute d squared of 0, I have to consider all the configurations from z to some point of index 0. All configuration of broken trajectories from z to an index 0 point. Okay, so this is the picture from the moduli space point of view, and this is the picture of the trajectories. And you want to prove that this is 0 or that this is even, if you work with z2 coefficients. And as you know, the trick is to use the gluing theorem that tells you that these trajectories are in fact grouped by pairs. So I drew this way. You have the gluing that tells you that all the configurations are grouped by pairs, but once you have that, you immediately forget who is related to who when you do the homology. You are happy because d squared is 0, and then you just forget how the things were related one to the other. So you don't care if the picture is like that or like that. It does not make difference from the homological point of view. But in fact, this information is very relevant to us. And it's half the information we need for the fundamental group. The other information comes when you introduce the augmentations. If I introduce augmentations, it again groups the things by pairs. Well, I'm cheating here because you don't necessarily have augmentation for all the points and so and so. But okay, the homology managed to clean the situation for you. But if you consider the points that do have augmentation, then they are grouped by pairs like that. And what you get is a cyclic order on the boundary, on all the points that are below z. Okay? From the Morse point of view. And this cyclic order is exactly the extra information you need to go from homology to homotopy. Because it gives you, the boundary of Z is just a linear combination of the points you have below it. And if you take the one-dimensional moduli space into account, you can see an order about these points below Z. This is somehow, I don't claim that this is a precise explanation of what I've done, but this is the main philosophy behind it. Okay, this is how I came to it. I don't know if it's enlightening, but okay, that's how it is. Okay, so maybe other questions? Oh, okay. One word about applications or partial applications. So let me come back to the exact case. Of course, you expect that this is related to this might be related to the Arnold conjecture, but not in the way I expected, in fact. Because we can see that we have generators for the fundamental group. But in fact, the generators are not the intersection points themselves. The generators are the steps. And it turns out that through one intersection point, you can have several steps. In the Morse theory, of course, the unstable manifold is connected. It's just a line. So in Morse theory, if you have one index one critical point, it gives you one generator. But in this setting, I see that for one intersection point, I can have several loops, several steps associated to it. So I define a kind of multiplicity for the intersection points, which are the number, which is the number of steps going through them. And I also have, unfortunately, a multiplicity for the base point, which is also, I have a non-trivial step. I would like to say a canonical step that starts from the constant disk to the, oh, by the way, I don't know if it's clear that what the picture of that is in the Morse setting, but in the Morse setting, how you do pick a base point. When you want to describe the fundamental group in the Morse setting, you pick the base point as being an index 0 point of your Morse function. But it's not so good, because if you want to move the function, the base point will move. So you don't do that. You put any point, and this point selects an index 0 point for you. You just follow the trajectory from the index 0 point to the minimum it's associated to. This is exactly what the special step does for us. I picked a base point. I did pick a base point, and it selects some index 0 intersection point with an augmentation associated to it. Okay, so this step always exists even in the Morse case, and in the Floer case, you may have other steps through the base point. So you have a multiplicity that is 0 in the Morse case, but can be non-zero in higher in Floer situation. And of course, you can just notice that you can define this multiplicity by counting pseudomorphic curves, by counting Floer strips, but it's a real count now. It's not the algebraic count. You just count each strip, +1 for each strip. And just a quick comment to say that, okay, the multiplicity of the base point is really unclear. It's not clear how it's related to the number of orbits, but you see that it's a count that only involves index 0 orbits, so you can somehow consider that this is in fact a count of multiplicities of index 0 orbits. But okay, anyway, if you count the number of index 1 critical points plus the base point with multiplicity, then you have at least as many of them as the minimal number of generators for the fundamental group. Okay? And what can I say? Of course, you can ask, is this necessary? Is the notion of multiplicity necessary? I don't know, it's great. One comment is that, of course, if you believe in the very strong version of, well, in one of the strong versions of the Arnold conjecture, you expect that you don't need any multiplicity here. But if you believe in the Arnold conjecture where you replace the Morse number by the stable Morse number, then you expect that this cannot hold without some multiplicity. Because in all the construction I gave also makes sense in the stable Morse. Well, maybe I should say what the stable Morse is. That instead of considering a Morse function on your manifold, consider a Morse function on your manifold times Rn, and you require that it's quadratic at infinity with some signature. Okay, and you can do Morse theory for that, and look what happens. And it turns out that in the, first of all, the construction I just gave, of course you have to define what an augmentation is and so, but it makes sense. Oh, everything makes sense. And it turns out that in the stable Morse setting, you have Morse functions that have strictly less critical points than usual Morse functions. So, at least in the stable Morse setting, you really need the multiplicities here. Okay? So there are two different questions. You can try to count the real intersections, and then it's very difficult to catch the number. But if you allow to count one with multiplicity, then you get exactly the number of generators of the fundamental group. Okay? And I don't know if there are questions. No questions? Okay. And another partial application, unfortunately, regards the Lagrangian cobordism. Because when you're doing cobordism, of course, you have the Ash cobordism theorem, but you also have the S cobordism theorem. So you are interested in the way the fundamental groups of the ends of the cobordism go into fundamental group of the cobordism. So what is the Lagrangian cobordism? Okay, so I said my manifold were compact, but it's a situation where it's not compact, it's not closed, but anyway. So I start with a Lagrangian, a symplectic manifold, and two Lagrangians in it. And the Lagrangian cobordism is a cobordism between my two Lagrangians, plus an embedding of this cobordism into C times M, and you put on C times M the standard symplectic form on C and the symplectic form on M. And you require that this cobordism is Lagrangian, this embedding is Lagrangian, and moreover, outside a compact set in C, the cobordism projects to the real line, and above the real line it's trivial, it's just the first Lagrangian times R, and above the positive reals, it's also a product. And you can ask how L minus and L plus symplectic invariants are related. And Biran and Cornea prove that if in the monotone case, then the homologies, the Floer homologies are the same. And in fact, and the proof is rather geometric. And you can ask what happens about the fundamental groups. And this is a joint work with Lara Simon-Suarez. That in the weakly exact situation, then the inclusion are onto. Induce surjective maps at the level of the fundamental group. And the proof is very similar to the proof for the Floer homology. What you do is you do, I will be very sketchy there, you do an isotopy that moves your cobordism in this situation, for instance, if you want to study the fundamental group of the minus infinity end, and you pick the base point over there, and you want to compute the fundamental group of W. And it turned out that you can take an almost complex structure such that the projection on the C factor is holomorphic. So if you have a strip, the projection in the C factor is holomorphic. The horizontal component is holomorphic. So it means that if you have a strip that starts here, the arrows indicate the direction of the strips. If I have the strips between these two things in C, it has to go this way. This way, I mean, plus infinity has to be on this side. and plus infinity on this side. And if I start from there, I can only go away. But because it's holomorphic, you have this maximum principle that tells you that as soon as you reach this unbounded region, you have to have infinite energy, and this is not the kind of strip we consider. Okay, so you have to be careful. Of course, I'm not using holomorphic strips with boundary on L0 and L1, but I'm using a moving boundary condition. So this moving boundary condition could draw a bound that I don't see. But in fact, because I use an homotopy in this direction and in that direction, here there is no moving. The moving boundary condition cannot stop my strip. Okay? So if a strip starts here, it can only stay in the fiber. And this means, of course, I didn't, yes, here above this point, I have just my Lagrangian L minus and a deformation of L minus. So it means that the fundamental group of the fiber and the fundamental group of W have exactly the same generators. Okay, all the moduli spaces I was interested in are exactly the same for L and W. I mean that when on the 1 times R cross R times 1 boundary component of the strip, I have boundary on W prime, but I can also move back to W. Okay? I have this curtain function. I have to go back, and I can start with on W and okay, but of course the trajectory is necessarily on the image of on the projection of the isotopy from W prime from W to W prime. So the boundary is somewhere in this region. It cannot be in this unbounded region. So okay, so this proves that this is an indication why the fundamental group should be the inclusion maps induce surjective maps at the level of the fundamental group. And notice that, in fact, why do I say it's a very partial application? Because this can be derived from Floer homology with local coefficients. This is by Baptiste-Chantraine, a remark by Baptiste-Chantraine and Lara. And okay, so if you use local coefficients, then I wanted to prove here, but it's not so complicated proof that, in fact, the maps have to be onto. The point with this proof is that there is no, this is somewhat algebraic, if you want, and this is purely exactly the same proof as for the homology. And of course, the good question is, what about injectivity? And for the injectivity, you guess that it's really crucial to control the relations. And because my relations depend on some Morse function and so, enfin, my description of the relations do not depend on this Morse function, but I cannot describe them without that. At the moment, I'm not able to prove that it's also injective, but conjecturally, at least, it should be injective. Okay, so I have 5 minutes to discuss some limitations of this construction and the problems I have, and I'm expecting help. Okay, so the main features you have, one of very important features you have in Floer homology is that you have continuation morphism. We have seen them appearing several times. You have these continuation morphisms, and you can make them compatible with the action and so with the filtration. Unfortunately, at the moment, I don't have such things for the fundamental group, which is a problem. So if you do a homotopy between your, everywhere I write H. In fact, it denotes all the auxiliary data I have. Okay. if you do a homotopy of the auxiliary data you used, in Floer homology you have this continuation morphism. Unfortunately, if you want to do the same at the level of the frontal group, you run into trouble, and I can explain the troubles. And things go like that. We try to do the same, exactly the same thing as before, as what we've done with the Morse case. We start with and let's say we have H0 and H1. Okay, we start with an H0 step, and we want to turn it into H1 steps. And what can we do? Okay, so this is my step. And what can we do? The only thing you can do is to start to grow an H1 perturbation. You introduce a moving boundary condition here where you use H1. And here you use the homotopy between H0 and H1. Okay? And you try to do that. And if you are lucky, then this breaks here. Maybe. But you may be not lucky. And if this happens, you can try to play the same game. And of course, if everything goes well, then here I see an H1 step, of course. But if I'm not lucky, the break can happen here. So the next step will not be an H1 step. It's not purely green. There is some red in it, which means I used H0 here. Okay? So this is the problem. You can, of course, you can explore the boundary of your moduli space and continue and do all the gluing, and it has to loop. Everything is fine. So you still get something, but the thing you get is not a morphism from the fundamental group associated to H0 to the fundamental group associated to H1. You get a morphism from this to something more complicated where H0 still plays a role. You cannot get rid of the initial Hamiltonian. Okay. So this is the. So there are two strategies then. Either you say, okay, that's life, and I define this more complicated fundamental group, a fundamental group that depends on two Hamiltonians, because there is something new here still, because the intersection point here that plays the role of an index 1 intersection point for H1 is an index 0 intersection point for H0. There is a shift in the indices, so you can try to play something with that. I did not think in that. The other direction is that, okay, that's how life is, and it's because you want to do too much at once. And you want to have this continuation morphism immediately. But there are situations where this construction works. In fact, it's when you, for instance, one situation is when you do a very small, you are in the generic situation and you do a very small perturbation. Then, of course, you understand all the moduli spaces, and this does not happen. You can really compare a Floer a step with associated to one Hamiltonian to a nearby Hamiltonian. It's very, okay, so this construction works for very small perturbation of generic situations. And then the question is only, how do you cross non-generic situations? And maybe doing all the crossings at once is not so evident. You should go check one bifurcation after the other. So you have to go through the bifurcation. And I was not brave enough to do that at the moment. Okay, so, but if you do that, maybe if you can be successful in crossing the non-generic situations, maybe you could get rid of these steps through the base point, because they appear just because I want to do this comparison with my Morse function at the very beginning. Okay, but this is just the connection. Okay, so this was a picture of the relations I did not show, so maybe I'll stop there. Thank you.